Hello, Organic Chemistry 22325. I love it. All right, this is one of my favorite topics of all time. This is our Claisen. We're going to actually hit 3 versions of our Claisen today. Claisen is just a general topic, general idea. It's named after a person, Claisen, but we're actually going to start with the basics. And then I've included some web links like I usually do. They're just towards the middle. So this process can get a little bit big. I've given you some links and some headings to look at. But let's start with just the basics first. I love tackling this second because our aldol, we've already got that down pat. In fact, we've already gone crazy with our aldol and then our 1,4 additions. And so I love Claisen second because now we're going to repeat an awful lot of what we saw in our aldol condensations. We're just going to apply it this time to an ester. So our Claisen is really the ester version of an aldol. All right, so let's try it. Let's start with just a general ester instead of an aldehyde or a ketone. And I want to point out a few things. I'm going to take my time with some of these steps before we get just a little bit too sassy. I'm going to point out with our esters that take a look at our reagents. We've got sodium methoxide in methanol, and you'll notice with our ether, they are all 3 matching. We're going to keep this scenario. I'm going to call that our matching base. We're going to use this base on purpose. Would other bases work? Absolutely. Except with our base, we'll see along our mechanism that our base can do 2 things. We can deprotonate here to form an enol or an enolate, but we can also react here. Our base can do 2 things. So if our base reacts here, look at this. It is absolutely matching right here what would be a leaving group. So when I say it matching, with esters, we always match our base to whatever the R group is on your ester. That way, something called a cross condensation or cross Fischer esterification or hydrolysis, but a cross hydrolysis doesn't happen. In other words, if I had ethanol, sodium ethoxide, as my base, I would end up with an ethyl here. So it is quite typical to match your reagents to your actual ester. So that's what I mean by matching. So we're matching. Now we've got 2 places we can react, but what's going to happen first in or productive at least, it could happen in any order, but with our sodium methoxide, we can generate an enolate with an ester. So with these, you can't just heat them. You do need the base. You need a little bit of help for these. Remember, aldehydes and ketones are a little bit more reactive than our esters. So with our ester and our condensations, it's not just heat. We have our matching base. So we're going to make this enolate, and it's still a good nucleophile. Esters, just like ketones and aldehydes, do have dual reactivity, so your enolate is a good nucleophile, and your ester can also be an electrophile right in that carbon. So just like aldehydes and ketones, we've got 2 different reactivities. So sweet Jesus, if you mix 2 of these, look at what you have. You've got an electrophile and a nucleophile right in the same mixture. So obviously they're going to react with each other. So how is this going to work then? Let's take our enolate and let's add an ester. And we'll keep it the same. Just like our aldol, we're going to react at our enolate, that is a good nucleophile, to our ester as an electrophile. So I'm going to go ahead and follow my pattern of numbering. Just like the aldol, we numbered 1, 2 on our nucleophile, 3 on our electrophile. Well, our esters, 2 for the price of 1, actually 3 for the price of 1. We had aldehydes, then ketones, now esters. We're going to do the exact same thing. The difference is our oxidation state or our oxidation level. Okay, look at our intermediate. What did we just make when we did this? Okay, let's color code our bonds like we usually do. We just did that. And then we just formed a bond out this way. And we just made this. All right, shut the front door. You already know what that is. Hold on a second. Let's make 2 major connections with Unit 2 and Unit 3. First of all, look at our spacing of our oxygens. This is the ester version of an aldol. There's your 1, 2, 3. All right, second, let's look at what we have right here. And that is a tetrahedral intermediate. Oh, I love it. All right, so what do we do every time we see a tetrahedral intermediate? We stop and we look for a leaving group. Well, in the case of an ester, you have a leaving group right there. So we're not done in this process. We're about to lose that leaving group. All right, let me keep my color coding so we can just kind of keep everything straight here that we're doing in this whole process. Okay, we just remade this double bond and we just lost I'm having a deep moment. Hang on. Look at what we just lost. Look at our leaving group. That matches our base. Okay, so now you can see we just matched our base and our leaving group. That's what I mean by matching base. Our leaving group is our base. Okay, so now let's look at our 1, 2, 3. And this is awesome because this has the same numbering as an aldol. All we did is go up an oxidation level. Our esters have one more bond to oxygen than our ketones and our aldehydes. And look at our aldol. Let's compare the two of them and let's compare the two oxidation states. Our typical aldol has our numbering like this, okay? And we have 2 bonds to carbon. And here we have just 1 bond to carbon, to oxygen. And then if we compare that to our claisen or our ester, now we've got 3 bonds to oxygen, and here we've got 2 bonds to oxygen. So if you take a look at all of them, they follow the exact same pattern. We're just up 1 level in oxidation. We've got 2 and 1, and then we've got 3 and 2. Awesome. And then, oh my gosh, wait for it. Haven't we seen these types of compounds in Unit 2? This is a beta keto ester. Okay. And now we know we can use those for things like our baker's yeast. They're a good starting material. Turns out that these beta keto esters are phenomenally useful. So just like our aldol, we don't have to stop here. In fact, we can take these products, these beta keto esters, and we can do stuff with them. So let's take our beta keto ester, and I've drawn this as a separate step because I want to draw the mechanism, but you can literally do this in all one reaction from your methyl ester all the way to this acetone. So again, I'm drawing it separate just for the mechanism. So let's take this and let's form our acetone. All right, the first thing we're going to do is actually the kickoff to our whole next unit. It's called a hydrolysis. Let me draw my beta keto ester here. And now we've got base. Our base can react in several places. And in fact, is it reacting in all of them? Probably. All right, over time though, with our sodium hydroxide and water, this is just like an acid-base reaction or an SN2 reaction that's in equilibrium. Over time, you are going to flood your whole reaction system with that OH minus. So could it add in here? Sure, but then it's a tetrahedral intermediate and you're going to lose it again. Can it add in here? Absolutely. But here's the difference between these two spots. Here, you have no leaving group. Here, you do. So that's what I mean by being productive. Are both happening? Absolutely. But let's go ahead and add our sodium hydroxide into our ester side. And let's draw that. Okay, so now we just formed a bond here. We have a tetrahedral intermediate. I love it. And now we're well versed at our tetrahedral intermediates. This is where our equilibrium principles come in. This is also where we look at the fact that we have probably 1 trillion sodium hydroxides in there, or hydroxide minus, versus everything else. So you're flooding your system. Could both of these be a leaving group? Absolutely. Could I lose this one over and over again? Yes, but I'm going to keep re-adding it. And then our productive one, then because of that numbers game, and the pKa difference between these two is really small. So are they both happening? Yeah. All right, let's go ahead and lose this one. Again, this is like Vegas. This one wins by sheer volume, by numbers. So what we just did was go to the carboxylic acid. So we're going to reform. Excuse me. I have some allergies today. We just formed this bond. And we left our ketone alone. So this overall process, we just added water. We went from an ester to an acid. This process is called a hydrolysis. We will see those a lot in this unit towards the end and the beginning of our next unit. All right, so now we've got this beta keto acid. Why is that important? Because this beta keto acid, in fact, it's so important, I want to redraw it down here. Our beta keto acid has a very particular relationship in space. If we rotate this bond, which we know that single bond is freely rotating, that bond is moving. So let's just move that bond. I'm going to draw instead like this. Okay, exact same structure. All I did was spin my bond. Okay, now wait for it. Look at this. You have a lone pair right here, and you have this beautiful hydrogen right there. That drawing was not as exciting as the way it sounded in my mind. Okay, we've got this beautiful lone pair and that hydrogen right there. And if you count what's in this ring, 1, 2, 3, 4, 5, 6, that is a 6-membered ring. It literally forms a 6-membered ring when you hydrogen bond that lone pair on this oxygen to the hydrogen right there. So when you have the beta keto acid, you can flip that bond around and you make a beautiful 6-membered ring with a hydrogen bond. This is the setup to our next step. So let's take a look at it. What we just did was the sodium hydroxide and water part. So now we want to make sure we've added some HCl back in to make sure that you have this hydrogen, because in theory, you have over here an O minus if you're in base, right? We have pKa differences. If you've got sodium hydroxide and a carboxylic acid, that's deprotonated. So we need to add that H back in. So we've added a little bit of acid. Now we've got this beautiful 6-membered ring, and now we add just a little bit of heat. So this is like our aldol, right? We have a second step when we add heat to an aldol. We have a second step with our esters, and this is so fun. Okay, wait for it. Are you ready? Let's draw some arrows. We are going to do a pericyclic reaction that, if you had me for OChem 1, this is like a Diels-Alder. If you haven't had your Diels-Alders, that's fine. When you have a process that works in a ring like that, and all of your arrows are spinning in a ring, not spinning, your mechanism is forming a ring like this. And it doesn't matter where you start because you're ending up in the same place. But this pericyclic mechanism is about to lose. Okay, wait, let's draw it and let's see if you can figure out. I'm going to draw it funny, then we'll draw it pretty. Okay, so these bonds stayed, but we just formed a second bond here. All right, and then we lost that bond to hydrogen. So what happened over here? All right, we still have this, except those electrons went here and here. Okay, all right, now that looks awful, but I hope you can see where the electrons ended up. Let's draw this pretty so you can recognize what we just made. We just made, let's color code. We just made carbon dioxide and the enol of acetone. Okay, so this was our product. Our carbon dioxide is a gas. So this again could be part of Le Chatelier principle. On this is where the productive side happens. Can you have all kinds of competing reactions? Absolutely, but the second you lose CO2, it is going to bubble out of solution and you're done. So what happens anytime you have this beta keto acid, you can make that 6-membered ring and you can literally lose CO2. It is a well-known process. It happens in biological systems all day long. You will see this happening in biochem. When you can set up that 6-membered ring like that, you can literally lose CO2. So out of this entire process, let's go back up to the front just for 1 second. I want to write out that this whole thing can literally look like this as one step. In the lab, you can literally add your base. You can, and have it in your matching solvent. You can add some sodium hydroxide. You can add a little bit of acid quench and some heat, and you go all the way to the ketone. Okay, now if you start from just the methyl ester and you end with acetone, which you just did was a really long synthesis of acetone, even though that's only one step, you would think, well, wait a second, why in the world is this even important? Well, it does happen in our biological systems. It's also a really good way to make a ketone. And in our second part, these beta keto esters are really, really easy to deprotonate right there. Do you ever notice in OChem 1, the pKa on a regular ketone is, what, 22 to 26 or so? On a beta keto ester, or 2 ketones there, but typically a beta keto ester, your pKa is down now like an alcohol or a water, 15 or 16. Our pKa really drops there. That is quite an acidic place. And in fact, this resonance here is often sitting as the enol. In fact, that actually prefers that enol. I think it was 70%. We drew it out in the beginning of our aldol section. I think it's about 70% enol, 30% not enol in that form. So holy crap, a lot just happened in there. We started with an ester and we ended with a ketone. All right, let's fast forward just a little bit and let's put that in a process. But let me show you why it's so important. So we can start, we'll draw the mechanism there, and we can add things to that beta keto ester. And then we can end up all in one step with a substituted ketone. So this is one of the first ways that this was used. Remember, the pKa here is quite low, so if you add base to this, you are going to make that enolate right away. So let's start there. Now, to which side does your enolate form? It doesn't matter. There is a difference, but you could, and there's been studies that trap that middle. I'm going to go towards the ketone side just because, but I wouldn't mark you off if you go either direction there. So let's go ahead and form that enol. Okay, so now we've got a really good nucleophile. We don't have to stop with just these like we made on that last video or that last slide, but we can use this now with any kind of alkyl halide. It turns out they'll do a nice SN2 reaction. We just expanded our version of a nucleophile for an SN2 again, and we can alkylate right in that spot. Let's color code again. Okay, I love it. Okay, now just wait for it. All right, put a little star here. If you still have a hydrogen there, you can do this twice. In fact, it's incredibly common to do that twice. And why don't we draw it single and then we'll draw it twice. So then now this second part of this reaction, right, you've just added something here. And then now what part do you lose if you are, oh, I erased my whole oxygen there. If we're about to add sodium hydroxide and then a little bit of heat and acid, we're about to lose that chunk as carbon dioxide. So let's go ahead and draw that. Let's be productive on adding sodium hydroxide. Again, can it add everywhere? Yeah. Can it deprotonate all over the place? Yeah. But the one over time that's going to end up swapping will be this one. Let's not forget we added our R group here. We're going to get that tetrahedral intermediate. All right, we already know what to do anytime we get a tetrahedral intermediate. Now this one's tricky because, you know, we're in base. Do you notice we're in base and all of our signs are negative? We're not protonating anything. This one is simply like Las Vegas. You have got a billion of these. So over time, that is going to win and stay in your compound, and you're going to lose that base. So what we have done, let's not forget we've added an R group there. So what we have done now is made the beta keto acid, except this time it is substituted. And now that last fourth step with a little bit of acid and heat means, all right, let's rotate this bond. Can we make a 6-membered ring there? We can. Okay, so let's draw it this time like this. And we still have our R group there. Beautiful. All right, so we can make this 6-membered ring. I like to draw in the hydrogen bond because it really shows the 6-membered ring. It also gets me started on this mechanism because this hydrogen is going to end up with that oxygen. So I like to start there. You can start there if you want to in your process. So I'm going to literally break this bond. Okay. And then how do we, let's see, how do we write that? We are going to end with this. And then we still have, wait for it, our R group attached to that, and then our CO2. And our CO2 is this and this. So the really important one and the tricky one to see is right here. You literally break that bond and you make CO2 and then you lose it as a gas. And then that's our product. So holy crap, we can literally go now, let's draw that out as one process. Wow, we could literally go from this to that. One step, that whole process. If we really wanted to be crazy about it, we absolutely could do that. Isn't that incredible? So what we're looking at is actually 3 different named reactions. We're looking at the acetoacetic ester synthesis, and we're looking at the malonic ester synthesis, and we're combining them. And so that is what's in my web links here that we're getting to. And just to give you a little bit of a diagram, maybe for your notes or your cheat sheet, remember you can start or stop. You can combine all of these processes. You can start with that almost like an aldol condensation. And here's your 1, 2, 3. And then you don't have to add anything. You can go straight to the decarboxylation. This is minus CO2, and you go right to that ketone. But you can also, in the middle of this synthesis, you're already in base. If you add any kind of alkyl halide, you're going to alkylate here, and then you can go straight to that substituted ketone. Now let's put a little 2 times in here. If you've got 2 equivalents of that, guess what? You can do that twice. So you can see why this is towards the end of the semester because we have a whole lot going on here. But you can also see why this is literally a 120-year-old reaction, but it is used all day, every day. These are dirt cheap reagents and a phenomenal way to make a nice substituted ketone in just a matter of 1 or 2 steps. Now, if you want to feel sassy in your synthesis, you can put it all in one step. If you want to spell it out like me, you can. And what I've tried to do, if you notice on my arrows, is I've done 2 different arrows, but I'll start with number 1, number 2, and then I'll end with 3 and 4. So you get the idea that they're all in the same synthesis. I think that's on the next problem. I'll show you that. So acetoacetic ester synthesis, I gave you some links there. That's the first part. Adding stuff to it is the malonic ester synthesis. So I've put that in there. And then finally, our third part, just for funsies, I put a year on that. Can you believe this chemistry has been around that long? 1894 is when the Dieckmann condensation came out. All right, so how do we define our Dieckmann condensation? What's rule number 2 and how to make organic too hard? Put a ring in it so you know where we're headed. Can this happen with a ring? Absolutely. So just like our aldol, can we have an enol somewhere in here, and can we form a ring? Yes. So let's treat this substructure with our base, and I am going to form this enolate first. Could you pick either one? Absolutely, they're symmetrical. All right, anybody want to guess what size ring we're about to make? Just like the aldol, oh my gosh, we're so trained. We make the bond between 2 and 3. So how do we know how big our ring is? 1, 2, 3, 4, 5-membered ring. I love it. I am just going to draw a 5-membered ring. How do we make that happen? Right here. Okay, so let's put in our 1, 2, 3. Okay, this is where it gets super fun. Is number 1 in the ring? No, it is not. So let's put our numbers in, 2, 3. Number 1 is outside. Number 1, we reformed that double bond. And then we formed our bond between 2 and 3. Okay. And then what is left on number 3? Well, we still have an OMe. And we have that O minus. All right, we have a tetrahedral here, tetrahedral intermediate. Let's lose our leaving group. And then what do we end up making? We make our product. Let me color code our product. Okay, here's our 1, 2, 3. Let's color code. We reformed that bond. We made this bond. And we reformed that. Okay, I love it. 1, 2, 3. Oop, and I think I just numbered backwards. Did anybody catch that? 1, 2, 3. There is our ring. All right, now this is the Dieckmann version of the acetoacetic ester synthesis, malonic ester synthesis. What does your gut tell you? Do you feel like if I threw in some base in an R group with an alkyl halide on here, we could alkylate that? Yes. So isn't this exciting? All right, we could add a little bit of base in there and add an alkyl halide. And how's that going to happen? Well, we're about to form, let's form an enolate here. Okay. How do you know where your enolate is going to form? Always between your oxygens. Your pKa is much lower here than anywhere else. So it doesn't matter what base you use. We are just matching our ester. But it doesn't matter what base you use. That's where you're going to deprotonate. And then this makes a really good nucleophile. So let's add our ethyl bromide here. I just kind of pick that. Okay, I love it. And now we've just alkylated. Let's color code a little bit. Okay, and then we still have our ester. There you go. There's our intermediate. And now check it out. This is all in the same reaction. We just did number 1 and number 2. Now, if you add some sodium hydroxide to that and then a little bit of heat, what is your product going to be? You're going to lose CO2. And where do you lose CO2? Let's number 1, 2, 3. You lose right there between 1 and 2, and you make your product. All right, these are so fun. I hope that this at least gave you a place to start to try to practice some of these. These are some of my favorites. So this is just defining our 3 variations. We need to do a bunch of problems on these, and we'll likely have these show up in our synthesis, and we'll have this process show up. Our hydrolysis will show up later.